Look, here's something that'll stop you cold. You've probably heard it 1,000 times. Matter is mostly empty space. The atoms that make up your hand, the wall in front of you, the chair you're sitting on, they're almost entirely nothing. The nucleus of an atom is tiny, and the electrons are even tinier, and between them, vast emptiness. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be gnats buzzing around the upper seats. Everything else? Empty. So here's the question that should be driving you crazy. If you're mostly empty space, and the wall is mostly empty space, why can't you just walk through it? Why does the wall feel solid? Why does anything feel solid? This isn't some philosophical puzzle. This is a real physical question about the nature of matter, and the answer, the real answer, is going to change the way you see everything around you. You might think, well, the electrons bump into each other, but that's not it, not really, because electrons aren't little balls bouncing off each other like billiard balls. They're not even particles in the way you think of particles. And the force that stops your hand from going through the wall, it's not contact in any normal sense. Nothing is actually touching. The truth is stranger and more beautiful than you've been told. It involves quantum mechanics, forces you can't see, and a principle so fundamental that it governs everything, from the stability of matter to the structure of stars. Feynman knew this. He spent his life explaining it, and in his lectures at Caltech, he showed us that the reason you can't walk through walls has almost nothing to do with space being filled up. It has to do with energy, with quantum rules that forbid certain things from happening, and with forces that operate at scales so small you can't even imagine them. By the end of this, you're going to understand why solidity is an illusion, but also why that illusion is absolutely real. You're going to see that the answer to this question opens the door to understanding chemistry, biology, the sun, and even the nature of life itself. This isn't abstract. This is the world you live in, explained at the deepest level. Every single day you experience solidity. You sit in a chair and it holds you up. You lean against a wall and it doesn't give. You pick up a glass and your fingers don't pass through it. This feels obvious. This feels like the way things just are. But stop for a second and really think about it. Solidity, what does it mean for something to be solid? You might say it means the atoms are packed tightly together. But that's not quite right. Even in the densest materials, steel, diamond, osmium, the atoms are still mostly empty space. The nucleus is unimaginably small, and the electrons occupy a cloud of probability around it, but the cloud itself is mostly nothing. If you could magically turn off the forces that hold atoms apart, you could compress a human body down to the size of a grain of sand. All the actual matter in your body, the protons, neutrons, and electrons, would fit in a space smaller than a dust mote. So the solidity you feel isn't about stuff being tightly packed. It's about something else. Let's start with the most obvious candidate, the electrons. When you push your hand against the wall, the electrons in the atoms of your hand get close to the electrons in the atoms of the wall. And electrons repel each other, right? They're negatively charged. And like charges repel. So maybe that's it. Maybe the wall feels solid because the electrons in your hand are being pushed back by the electrons in the wall. That's part of the story. But it's not the main part, because if it were just about electric repulsion, the force would drop off quickly as you moved your hand away. The repulsion between two charged particles follows an inverse square law. Double the distance, and the force drops to a quarter. But the solidity of matter doesn't feel like that. It feels like a hard boundary. You push, and the wall pushes back with an almost infinite resistance. Why? Here's where it gets interesting. The real reason you can't push your hand through the wall has to do with quantum mechanics. Specifically, it has to do with the Pauli Exclusion Principle. This is one of the most important. rules in all of physics, and Feynman talked about it constantly. It's the reason matter is stable. It's the reason chemistry works. It's the reason you exist. The Pauli Exclusion Principle says this: no two electrons can occupy the same quantum state at the same time. What does that mean? Every electron in an atom has a set of quantum numbers, properties like energy level, angular momentum, and spin. And the rule is that no two electrons in the same atom can have identical sets of numbers. They have to differ in at least one way. Now, this might sound like a technical detail, but it has huge consequences. Because of this rule, electrons can't all just collapse down into the lowest energy state. They have to stack up, filling higher and higher energy levels. This is why atoms have structure. This is why the periodic table exists. This is why different elements have different chemical properties. And here's the kicker: the Pauli Exclusion Principle doesn't just apply within a single atom. It applies everywhere. When the electrons in your hand get close to the electrons in the wall, they're not just repelling each other electrically. They're being forbidden from occupying the same space by the exclusion principle. The electrons in the wall are already occupying certain quantum states, and the electrons in your hand can't occupy those same states. They're blocked, not by a physical barrier, but by a quantum rule. This is what gives matter its rigidity. This is what makes the wall feel solid. It's not that the wall is full of stuff. It's that the quantum states are full. The electrons in your hand literally cannot be in the same place as the electrons in the wall, because the rules of quantum mechanics forbid it. Let me say that again because it's so important. Solidity is a quantum phenomenon. It's not about particles bumping into each other. It's about the quantum states being occupied. The wall resists your hand because there's no room in the quantum state space for your electrons to go. Feynman explained this beautifully in his lectures on quantum mechanics. He pointed out that if you could somehow turn off the Pauli Exclusion Principle, matter would collapse. Atoms would shrink down to almost nothing. All the electrons would fall into the lowest energy state, and you'd have a tiny, dense blob instead of the structured, stable matter we know. The exclusion principle is what keeps atoms big. It's what keeps matter spread out. It's what gives the world its size and shape. But let's dig deeper. Why does the exclusion principle exist? What's the underlying reason for it? This is where Feynman really shone, because he didn't just state the principle, he explained why it had to be true, based on the fundamental nature of particles. Electrons are fermions. That's a term that describes particles with half-integer spin 1/2 in the case of electrons. And there's a deep connection between spin and statistics, the mathematical rules that govern how particles behave. Fermions obey what's called Fermi-Dirac statistics, and one of the consequences of this is the Pauli Exclusion Principle. But why do fermions behave this way? It comes down to symmetry. When you have two identical particles, quantum mechanics says that the wave function describing the system has to be either symmetric or anti-symmetric under the exchange of the particles. If you swap particle A and particle B, the wave function either stays the same, symmetric, or flip sign, anti-symmetric. Fermions have anti-symmetric wave functions. Bosons, particles with integer spin like photons, have symmetric wave functions. Now here's the thing, if two fermions are in the exact same quantum state, swapping them doesn't change anything. But the wave function has to flip sign when you swap them. The only way to satisfy both conditions is if the wave function is zero. In other words, the probability of finding two fermions in the same state is zero. It's not unlikely, it's impossible. This is the deep reason behind the Pauli Exclusion Principle. It's baked into the quantum nature of fermions. And because electrons are fermions, they obey this rule. And because they obey this rule, matter is stable and solid. So when you push your hand against a wall, what's really happening? The electrons in your hand are getting close to the electrons in the wall. Electric repulsion starts to push back, that's part of it. But more fundamentally, the quantum states are filled. The exclusion principle says the electrons can't occupy the same states, and so they resist being pushed closer. The resistance you feel is a quantum mechanical force. It's not contact in the classical sense. It's the universe enforcing the rules of quantum mechanics. And here's something even more mind-blowing. This same principle is what holds up a white dwarf star. When a star runs out of fuel and collapses, gravity tries to squeeze it down to nothing. But the electrons resist. They obey the exclusion principle, and they can't all be forced into the same space. This creates what's called electron degeneracy pressure. It's a pressure that arises purely from the quantum rules, not from temperature or motion, and it's strong enough to hold up a star for a while. If the star is too massive, even degeneracy pressure isn't enough, and it collapses further into a neutron star or black hole. But for stars below a certain mass, the exclusion principle is what keeps them from collapsing completely. In a neutron star, it's the neutrons, also fermions, that provide the degeneracy pressure. The same quantum rule that keeps your hand from passing through a wall is what keeps a neutron star from collapsing into a black hole. The scale is different, but the physics is the same. That's the beauty of it. The same fundamental principles operate everywhere, from the tiniest atoms to the most massive stars. Let's talk about energy now, because that's the other critical piece. When you try to push two atoms closer together, you have to do work. You have to add energy to the system. And the atoms resist because pushing them closer means forcing the electrons into higher energy states. Remember, the low energy states are already occupied. To get any closer, the electrons would have to jump to higher energy levels, and that requires energy. This is why compressing matter is hard. It's not just about overcoming electric repulsion. It's about climbing up the ladder of quantum energy levels. Every step up requires more energy. And as you squeeze harder, the energy cost gets higher and higher. Eventually, you reach a point where the energy required is so enormous that you can't go any further, unless you have something like the gravitational force of a collapsing star. Feynman emphasized this point over and over in his lectures. Energy is the currency of physics. Everything that happens involves energy being exchanged or conserved. And the structure of matter, the fact that it's stable, that it resists compression, that it feels solid, is all about energy levels and quantum states. Now, here's a question. If matter is held together by quantum rules and electric forces, why doesn't everything just fly apart? Why are atoms stable at all? This brings us to the forces at play inside an atom. You've got the positively charged nucleus in the center and the negatively charged electrons around it. Opposite charges attract, so the electrons are pulled toward the nucleus. But they don't fall in. Why not? In classical physics, this was a huge problem. If you think of electrons as little particles orbiting the nucleus like planets around the sun, they should radiate energy and spiral inward, crashing into the nucleus in a fraction of a second. But they don't. Atoms are stable. This was one of the great mysteries at the turn of the 20th century, and it was one of the things that led to the development of quantum mechanics. The answer is that electrons aren't orbiting in the classical sense. They're described by wave functions, probability clouds that tell you where the electron is likely to be found. And these wave functions correspond to specific energy levels. The electron can only exist in certain states with certain energies. It can't have just any energy. This is called quantization, and it's a fundamental feature of quantum mechanics. The lowest energy state, the ground state, is stable. The electron can't fall any lower because there's no lower state to fall to. It's stuck at the bottom of the energy ladder. To move to a higher state, it needs to absorb energy, from a photon, for example. To drop to a lower state, it emits energy, but it can't go below the ground state. That's the floor. This quantization is what makes atoms stable. The electrons are in specific, allowed states, and they can't collapse into the nucleus because there's no quantum state that would allow it. The exclusion principle prevents multiple electrons from piling into the same state, and quantization prevents them from collapsing altogether. So the picture of an atom isn't a little solar system with electrons whizzing around. It's a nucleus surrounded by clouds of electron probability, with the clouds corresponding to different energy levels. And the electrons are spread out over these clouds because of the uncertainty principle. Another quantum rule that says you can't know both the position and momentum of a particle with perfect precision. The more you confine an electron in space, the more uncertain its momentum becomes, which means its energy goes up. So there's a balance. The electron spreads out enough to minimize its energy while still being bound to the nucleus. All of this, quantization, the exclusion principle, the uncertainty principle, works together to create stable matter. And the solidity you feel, the resistance of the wall, is the macroscopic consequence of all these quantum rules operating at the atomic level. Let's zoom out a bit. Think about chemistry. Why do different elements behave differently? Why does carbon form 4 bonds while oxygen forms 2 and helium doesn't form bonds at all? It's all because of the electron structure, which is determined by the exclusion principle and the energy levels. Electrons fill up the energy levels in a specific order, and the outermost electrons, the valence electrons, are the ones that participate in chemical bonding. Carbon has 4 valence electrons, and it can share them with other atoms to form bonds. Oxygen has 6 valence electrons, and it wants to gain 2 more to fill its outer shell. Helium has 2 electrons in a completely filled shell, and it doesn't need or want any more, so it doesn't react with anything. The entire periodic table, all the diversity of chemistry and material properties, comes from the way electrons fill up the quantum states. The exclusion principle determines the structure, and the structure determines the chemistry. It's all connected. And here's something Feynman loved to point out: the same rules that explain why you can't walk through walls also explain life. Because life is chemistry, and chemistry is quantum mechanics. The molecules that make up your body, DNA, proteins, enzymes, they all depend on the precise arrangement of atoms, held together by chemical bonds, which are held together by the quantum rules governing electrons. When an enzyme catalyzes a reaction in your cells, it's doing so because the electron clouds of the enzyme and the substrate fit together in just the right way. The shapes matter, and the shapes are determined by the quantum states of the electrons. When DNA replicates, the base pairs bond together because of the precise quantum interactions between the electron clouds of the nucleotides. Life is quantum mechanics in action. You are a walking, thinking consequence of the Pauli Exclusion Principle. Now, let's push even further. What about forces? We've talked about the exclusion principle and quantization, but there's still the electric force to consider. The repulsion between electrons and the attraction between electrons and the nucleus, these are electromagnetic forces. And Feynman spent a lot of his career thinking about electromagnetism at the quantum level. That's what quantum electrodynamics, or QED, is all about. In QED, forces are mediated by particles. The electromagnetic force is carried by photons. When 2 electrons repel each other, they're actually exchanging virtual photons. These aren't photons you can see or detect directly. They're virtual particles that exist only for a fleeting moment, allowed by the uncertainty principle. But they're real in the sense that they carry momentum and energy, and they're what transmits the force. So when your hand pushes against a wall, and the electrons in your hand repel the electrons in the wall, what's really happening at the quantum level is a flurry of virtual photon exchanges. The electrons are sending photons back and forth, and the net effect is a repulsive force. It's not contact, it's communication through photons. And here's the beautiful part. This isn't just a metaphor. It's the actual mechanism. Feynman developed the mathematical tools, Feynman diagrams, to calculate the probabilities of these interactions. You can draw a diagram showing two electrons exchanging a photon, and you can calculate the force that results. And the answer matches experiment to incredible precision. QED is one of the most accurately tested theories in all of science. So the solidity of matter, the reason you can't walk through walls, is ultimately about quantum rules and electromagnetic forces. The exclusion principle keeps the electrons from occupying the same states. Quantization keeps the atoms stable, and the electromagnetic force, mediated by photons, provides the pushback when things get too close. But there's one more layer to this. Let's talk about the nucleus. The protons in the nucleus are positively charged and they repel each other. So why doesn't the nucleus fly apart? What holds it together? The answer is the strong nuclear force. This is a different force from electromagnetism, and it's much stronger, hence the name. The strong force acts between protons and neutrons, and it's what binds them together into a nucleus. It's a short-range force, only operating over distances of about a femtometer, that's 10⁻15 meters, about the size of a proton. But within that range, it's incredibly powerful. The strong force is mediated by particles called gluons, and it operates between quarks, the particles that make up protons and neutrons. This is quantum chromodynamics, or QCD, and it's even more complicated than QED. But the principle is the same. Forces are carried by particles, and the interactions can be calculated using quantum field theory. So the nucleus stays together because the strong force overcomes the electric repulsion between protons, and the atom stays together because the electromagnetic force attracts the electrons to the nucleus. And matter stays solid because the exclusion principle prevents electrons from overlapping. It's a hierarchy of forces and quantum rules, all working together. And here's the truly astonishing thing, all of this, every force, every interaction, every quantum rule is described by a handful of equations. The standard model of particle physics encapsulates all the known forces except gravity and all the known particles. It's a single unified framework that explains everything from the stability of atoms to the collisions and particle accelerators. Feynman contributed enormously to this framework. His formulation of QED, his diagrams, his path-integral approach to quantum mechanics, these are foundational tools in modern physics. And he always emphasized the unity of nature. The same principles apply everywhere. The same forces operate at all scales. The same quantum rules govern electrons in your hand and quarks in a neutron star. So when you ask, why can't I walk through walls, you're really asking about the nature of matter, the rules of quantum mechanics, the forces that hold atoms together, and the deep symmetries that underlie all of physics. The answer isn't simple, but it's beautiful. And it connects everything. Every time you touch something, every time you feel resistance, you're experiencing the macroscopic effects of quantum mechanics. The solidity under your fingertips is the Pauli Exclusion Principle at work. The pushback you feel is virtual photons being exchanged. The stability of the object is quantization and the strong force. It's all real, it's all measurable, and it's all explained by the fundamental laws of physics. Feynman loved to remind us that the world is comprehensible. You can understand why things are the way they are. You can trace the chain of reasoning from everyday experience down to the quantum level and back up again. And when you do, the world becomes richer, stranger, and more wonderful. The next time you lean against a wall, think about what's really happening. Think about the electrons in your skin approaching the electrons in the wall. Think about the exclusion principle forbidding them from occupying the same quantum states. Think about the virtual photons being exchanged, carrying the electromagnetic force. Think about the nuclei held together by the strong force, and the atoms held together by quantization. You're not just touching a wall, you're interacting with the quantum fabric of reality. And the fact that the wall holds you up, that it feels solid, is a consequence of the deepest laws of nature. This is what Feynman meant when he said that science doesn't diminish the beauty of the world, it enhances it. Knowing the reason behind the solidity of matter doesn't make it less real or less impressive. It makes it more impressive, because now you see the intricate dance of forces and quantum rules that makes it possible. You see the elegance of the underlying principles. You see the connections that tie everything together. And you realize that the question, why can't I walk through walls, isn't a silly question at all. It's a profound question. And the answer reveals the fundamental nature of reality. So the next time someone tells you that matter is mostly empty space, you can smile and say, yes, but the empty space is full of quantum rules. And those rules are what make the world solid, stable, and real. They're what make life possible. They're what make you possible. And that's the beauty and the terror of it. The same exclusion principle that keeps your hand from passing through a wall is what keeps atoms from collapsing. The same forces that hold molecules together are what allow enzymes to function, DNA to replicate, and your brain to think. The solid world you experience every day is a macroscopic illusion built on quantum rules. But it's a real illusion. It's as real as anything can be, because reality at its deepest level is quantum mechanical. And the solidity of matter is one of the most beautiful demonstrations of that truth.